Hey y'all, how's it going today? So today we're going to be talking about color. Right, so this is kind of what I'm calling color part one. And I really want to start off today. This is just like a little introductory video. I've got some other stuff that you guys are going to run through, watch some other videos, do a little bit of reading, have some kind of constructed questions that you guys are going to be answering. But I want to start off by I need everybody to go ahead and close your eyes. I just want you guys, I want to start this off by being thankful for the fact that we have these organs, our eyes, that can actually sense and perceive certain frequencies of electromagnetic waves. Right? Within the visible light range, our eyes can pick up and sense these electromagnetic waves. Just oscillating electric and magnetic fields. And our eyes can pick that up and allow us to see. And if you want to know how big of a deal this really is, what you can do, and I recommend doing this, it's kind of fun, is if you clear out kind of like a room, like your living room or something, and you close your eyes, you can even put on like a bandana, and you have someone like spin you around a bunch of times and spin you in different directions, and then try and like walk somewhere. But be careful because it's quite dangerous. You are so reliant on your vision and just your sensory organs in general, but especially our vision. We are so reliant on that to see and sense the physical material world around us, the matter around us, and where it is, right? Those solid things. So something to keep in mind, something to be thankful for. Now, I want to also talk about how there's three main things that electromagnetic waves can do, really. And one of the videos you're going to watch is going to talk about this, but they can either, when we have an electromagnetic wave coming in and interacting with matter, right, it can either reflect off of that matter. Okay, so it can reflect. It can transmit, so it can go through. And sometimes it transmits cleanly and goes straight through. Sometimes it gets scattered a little bit. Sometimes it gets bent. Or it can be absorbed. So those are the three things that can really happen. It can reflect, it can transmit, or it can be absorbed. Okay. So that's something to keep in mind as we're talking about this. Now, I want to begin our discussion. I actually was messing around this morning with some prisms. Right? I brought a set home from the classroom, and I was kind of messing around with them in the sunlight coming in through the window. And here's a little video that I recorded of that. Let's see if it'll let me play it maybe. If I move myself over here. There we go. Right. So here we have, it's a nice sunny morning. We've got the sunlight coming down through the prism. And right from the sun, and we have all these different waves of electromagnetic radiation coming down from the sun. And as it goes through this prism, on this piece of paper is projected, right? It's projected the electromagnetic waves coming from the sun. Right, is what is actually projected there. And this is what we end up getting. This is, I kind of zoomed in and turned down the brightness on my camera. And this is what we get. We get a rainbow. And it's just one of the most beautiful things you'll ever see. It's just gorgeous sitting there. You go from this beautiful red, kind of this orange, yellow, this cyan, this green, cyan, blue, and then even down into violet. It's really quite something. And what happens is actually there's the wavelengths beyond this as well, which would be over here. There'd be some infrared over here, and there'd be some ultraviolet over here, and everything in between coming in from the sun kind of splits up and divides, right? When I'm just looking at the sun, it's all those wavelengths combined, kind of gives it this white light characteristic. But when it goes through that prism, it actually kind of splits them. When it transmits through that prism, it kind of bends those different wavelengths, and they spread out away from each other, right? And we get this rainbow. But those colors that you see right there, the Roy G. Biv, it's a figment of your imagination. Those colors are in your mind. They are in your head. Now, not the electromagnetic waves, no. The actual wavelengths themselves that are coming into your eye, those actual electromagnetic waves, those are real. Those are real as real can be. If you were to close your eyes, they would still come up and they'd still hit your eyelids, right? But the actual color, that actual redness, that blueness, that greenness, that is come up with in your head. Right? That is your brain that is actually creating those things, creating those images, allowing you to see them. So it's a little bit of a mind trick. And what's interesting is there's this cool combination of both your physical biology, right, that allows you to perceive these wavelengths in your eyes, and how your brain actually processes them. So there's actually like birds, for example, that can see, they can perceive these wavelengths in the infrared and in the ultraviolet. They can actually see some of those. Now, what colors do they see? Do they see colors? We actually don't even know that. It's hard for us to say if they see the exact same colors that we do. They may not see red. They may be able to perceive these wavelengths that are red, but they might not be able to see them as red, right? They may not know them because their brains work differently. So this is where it's interesting. I want to stress that idea. This is a physical, right, electromagnetic wave. It's a real thing. It's a real, right, wavelength. It's a frequency. It has an energy value, right? But the actual colors themselves, right, those are colored in my mind, in my brain. Kind of trippy. Now, starting off here, looking at this, we have our electromagnetic spectrum. And it's just this little slice, right? We've got ultraviolet over here, infrared over here. Here are radio waves. Here are gamma rays and whatnot. And here's the spectrum, right? Going from red at the longest wavelength, around 700 nanometers, down to violet at around 400 nanometers, right? So within that range, this happens to be the range that our eyes are able to see. Our eyes are able actually to pick up, and we're going to go over how they do that in a second. But I want to start with this little plant, right? And this little plant. And I see this plant as it's got these beautiful green leaves, right? Well, why does this plant have green leaves? In order to understand that, we need to understand, well, how is this plant interacting with this light coming down from the sun? So we have all this visible light, all this ultraviolet, all this infrared coming down from the sun or from the light in the room, right? And it's bouncing off of the leaves of this plant, right? It's interacting with the molecules that make up this plant, okay? Molecules and those cells. And within these cells, right, there's a lot of molecules that aren't really affected by the light. They don't absorb it. They just let it transmit, or they reflect it. But there's a few specific pigments, right, some molecules that are produced by the plant called chlorophyll. There's chlorophyll A and chlorophyll B. And this is a graph of how much they're absorbed, right? So here it's really absorbed, and here it's not that much absorbed, and the wavelength of light. So we can see that these chlorophyll pigments really absorb these kind of blue and violet wavelengths of light, 400 to 500. So if I have an electromagnetic wave in that range that comes in towards the plant, it hits those leaves, and those leaves absorb that energy and use it to transfer it to store that energy in the bonds of sugars, right? Similar with the range from 600 to 700 nanometers, right? Wavelengths in that range are also absorbed, right? But those from about 500 to 600, right, are not absorbed, right? They are actually, in this case, they are reflected. Right? They're going to be reflected and or transmitted. In this case, it's reflected. And so those wavelengths, 500 to 600, right, nanometers, come down, they hit these leaves, they go from these leaves, and they bounce off into my eye, right? Now, in my eye, I happen to have, right, 3 different types of cone cells, 3 different types of cells in the back of my eyeball, in the retina, right, that are each a little bit different, right? One type of cone cell, right, the blue cone, or the short wavelength cone, has and they all have these opsin proteins, right, which are proteins kind of like a chlorophyll, right, pigment proteins. And this opsin happens to be able to be sensitive, happens to be able to absorb wavelengths around 420 to 440 nanometers, right? The green cone, or the medium wavelength cone, has a sensitivity and max absorption around 534 to 545 nanometers. And the red, or the long wavelength cone, has a sensitivity and max absorption around 564 to 580 nanometers. Right. So here, off of this plant, we have reflecting this area around 500 to 550, right, we'll say. So if we look at these short, medium, and long, these blue, green, and red cones in my eyes, and their kind of sensitivity, where they absorb the most and where they absorb the least, this is what we get, right? So this, let's say 525, let's say I have a wavelength of around 525, right, bouncing off of here and coming into my eye. Well, what happens is that those wavelengths, right, that wavelength, that 525 nanometer wavelength light comes into my eye, and it is absorbed a lot by this medium wavelength cone, right? So that kind of tells me you're seeing a little bit of green, right? Seeing a lot of bit of green, right? And then it's absorbed some by this long wavelength cone, which is saying, hey, you're seeing a little bit of this like yellowish red, right? Reddish. And it's absorbed just a little tiny bit by this blue, right? So that's saying, hey, you're getting like a little bit of blue there. Hey, buddy, right? And so the combination of how much this cone is stimulated, how much this cone is stimulated, and how much this cone is stimulated, that combination tells my brain that I'm seeing what I call green, right? What is actually this wavelength, this specific wavelength. My brain says green. Now I could actually trick my brain, right, by just shining some like green lights, a little bit less of this red light and a little bit of blue light. I could actually trick my brain, and you guys will mess around with that, trick my brain into thinking that I'm seeing a wavelength at this range when actually I'm seeing multiple different wavelengths in different amounts, right? But that's how my brain is actually making up that I'm seeing this color, because different cells in my eyes are being stimulated by different wavelengths in different amounts. So if you look at this pot here, right, this kind of like nice purple pot, right? Well, here, let's say that's more around like 425, right, is the wavelength that's coming off into my eye. So that's mostly stimulating the short wavelength of this blue cone. But there's a little bit of stimulation on the red, a little bit of stimulation on the green cone. And so my eye, my mind perceives that as being violet, as being purple, right? Similar if I had something like a nice orange Frisbee here, right? Well, that might be right here around 600, right, nanometers. That's actually reflecting off of here and coming into my eye. And so in my eye, this long wavelength cone is stimulated. This medium wavelength, this green cone is stimulated. So I got red stimulated a lot, green stimulated a little bit. So my brain says, oh, it's orange, right? This is not like orange. Okay? A dog would not see this as orange. A dog would not be able to see this as orange, but it would, right? It is still a wavelength coming off at around 600 nanometers. Okay? It's incredible, but it's all about perception. Our brain is what actually takes the stimulation of these different cone cells from these wavelengths. Our brain turns that stimulation into a color that we see. Okay. Now, we all kind of see those like relatively universally. We have a lot of the same underlying biology. However, things in our biology can go wrong. And I say this from a place of personal anguish and pain, because I am partially colorblind. I know, right? I didn't know for the longest time because I'm only partially colorblind. I'm on the red-green colorblindness spectrum. I'm not so bad. It's not like I can't see reds. I can actually see red, like this here. That is red. I see it as red, right? And my eyes can actually pick up those wavelengths, right? So there's none of these wavelengths that are on here that my eyes wouldn't be able to pick up. However, right, my red wavelength cone is deformed, right? My opsin protein here, my red opsin protein, is deformed. And so the curve that I get here for my long wavelength or my red wavelength cone is different, right? So I have a harder time kind of sometimes separating out if I had, a particular wavelength. I might have a harder time saying exactly what that is. I might have a harder time differentiating between two different shades of red, right? I noticed a lot, I have a hard time sometimes differentiating between light yellows and light greens, right around there. Sometimes I have a hard time between dark blues and dark purples. I have a hard time with that, right? And it has to do with the shape, right, of my long wavelength of this absorption spectrum, because my red opsin is deformed, right? Now you can actually test this on yourself using like a color blindness test, and you can look these up kind of online. They're all over the place, and what you can get is you get these kind of colored plates like this. It's all these dots that are assembled, and you're supposed to be able to see a number in them. So most of you guys should be able to see that, like this guy, for example, very obviously 12. Even I can see this one. This is called like a kind of standard plate that everybody should be able to see, even if you can't see color at all, right? But then the other ones, you should be able to see a number in them, and this is where it gets really, really hard for me. And this is actually, I first found out, I was watching a show called Brain Games where they did one of these, and I failed, and I was like, what is going on? So for example, I can see that this one is a 2, right? It's kind of faint, but I can see it. But the other ones, I got nothing, right? I cannot. I can see maybe some glimmers of what could be numbers. For example, I see like something like here possibly, but I don't have nearly enough. Maybe something like here. Maybe that's like part of a 4, but I don't really have enough to really be able to definitively say what those numbers are. And that's not because there aren't these wavelengths that are coming off of here, right? And this is actually a little bit different because since it's a digital screen, it's a combination of different colors and different amounts that my brain is supposed to think is a color. But even if this were on paper and it was just those wavelengths reflecting into my eye, I'd have a hard time with this, right? And it's not because those wavelengths aren't coming in and hitting my eye. It's because that my eye doesn't have the ability to suss out the differences between those wavelengths. Because the way that my brain is creating color is based on how those cones in my eye are being stimulated. And because of my deformation within those cones, mine are stimulated in a little bit of a different way. So I'm not able to perceive the same reality that some of you guys are. Okay. So that's something to keep in mind. What I'm going to have you guys do today is you're going to be walking through this lesson. There's a few different videos for you guys to watch, and a few questions for you guys to answer with those. A little book reading that I want you guys to check out. Make sure you dig that up. This is my favorite video by this guy, Steve Mould. It's about kind of why you can't take a good picture of the rainbow. And here he talks a lot about how, for example, we can see colors like on our screens and how they use pixels and different red, green, and blue pixels to allow us to see a wide range of colors to kind of stimulate actual wavelengths that we might actually see in nature, right? Which is kind of cool. And then there's a little simulation you can play around and then a few kind of follow-up questions. So that's that. I hope you guys enjoy. I hope you guys have fun. Appreciate the color, appreciate the world, be curious about it, ask questions, and I will see you guys next time.